Thank you very much, Charlie, for sort of marking the milestones of the department. And thank you also, Helmut, for coming, and your children as well for coming today. Thank you very much. It's a real pleasure to welcome you to this event and to the department and the newly named in one building. So I'm delighted. I think somebody then decided, well, Paul's got off quite lightly today, so we'll get him to predict the next 50 years. Genuinely, I think that's what happened. So it is my sort of job as the current head possibly to be looking forward to what is the future going to look like, what are we going to be doing in computer science in the next 50 years. And I thought it'd be useful to think about actually just the sheer possibility of predicting the future. So here's some things which were predicted to have happened by now. Anybody enjoyed Back to the Future? Hoverboards did not happen by 2020 or 2015 even. And also a famous futurist from 1999, Kurzweil, predicted there would be no books. Okay. Well, we kind of have books. We kind of have, sort of no books. We have digital documents and things, but honestly, you still see plenty of people still with a physical book. So predicting what definitely will happen is quite difficult. But also what's missing is the things that did happen that we didn't predict at all. Way back in 2004, 2005, was it? The iPhone came out. Nobody saw that coming. Okay, absolutely nobody saw that coming. This idea of a smartphone with a touch screen with gestural interactions, it wasn't predicted. And my field is human-computer interactions, so I'm interested in interesting interactions. So I went back to my books. I've got one called HCI in the New Millennium. That came out in 2002. Nothing about touch phones, screens, nothing like that. Smartphones were not on the radar in 2002. And I also looked at another one, which was HCI in 2020 and beyond, which was published by the ACM in 2008. And smartphones were vaguely mentioned a little bit, but they didn't mention anything like Twitter or Snapchat. And Twitter's fascinating because, in fact, in the 2020 book, it was actually saying it actually had a brief explanation of what Twitter was for those of you who hadn't come across it. So it was basically a micro-blogging service as an easy way for people to keep in touch with friends, family, and co-workers. Nothing about presidents using it to announce policy. Okay, and all the rest of what Twitter has enabled in terms of sort of popular rebellion, but also misinformation and toxicity. So we really weren't predicting things very well. And Snapchat is another example of a social media, which is why would anyone do a system where the messages disappear as soon as you read them? Well, ask any teenager. I've tried. Yeah, we predicting the future. What am I meant to do? How am I meant to predict the future? Because computer science is a science of the artificial. I can't, unlike physics, there may be problems about the universe which we've got to continue to look at and try to understand, and we can maybe predict, make progress on. What can I predict human creativity will come up with in the next, 5 years, let alone 50 years? So what I've done instead is to sort of think about where we are at the moment, our vision, which Charlie's briefly touched upon, of our vision for doing safe, ethical, and secure computation. I think this is what we're really good at as a department, is thinking about these aspects of safety, aspects of what it means to do things well for a good system, and doing it securely. And these are things that were strong in the department, and I can see now are rooted in the history of the department, as we've seen today. I could go through the department and go through the strategy more carefully. I've turned into a management wonk. I've got a strategy, I'm going to walk you through it. I don't think that's helpful. I think we need to think about, I could turn it into a list, and I don't think it'd be very edifying. But I thought what I would put out is actually there's two principles that we've also thought about as a department. Is that one of the key things that really we are thinking about as a department is when I've spoken to the department in, say, Research Away Days and other contexts and the staff, what we'd like to achieve as an academic body, people talk about doing meaningful work, doing something meaningful. And again, that fits back with Ian Wan's vision of you can do theoretical work, but it's applicable. We want to do interesting fundamental research, but we want it to matter and to make a difference out there in the real world. We want it to benefit society, and we want to inspire and educate our students to do the same. So I think I'd take those principles and I sort of think about those in the context of the future. I can't predict the future. Well, the internet can predict the future, so go on the website of your choice and take a pick what the future might look like. But I think I can predict some things which might be considered to be invariants. And a disruptor, which I can see standing here now. By invariance, I mean sociological invariance. They aren't invariance in the sense of the conservation of momentum or energy in physics, They're invariants in the sense that they seem to be how the world works and will probably continue to work for a way to come. And then, therefore, what is computer science's place in responding to those invariants? But I'll also signal a disruptor as well, because that sort of thing can change everything, and we'll go through that. The first invariant, we've been touching upon this indirectly in the sense of when I made a little joke about the computer that Ian Wand was leading on, Moore's Law. And Moore's Law has lots of different interpretations. You can take it in lots of different ways. But basically, the general rule is computational power doubles every 2 years. And this was based on an observation made by Moore in the 1970s, having looked at what he foresaw as the miniaturization of transistors. So on the basis of that, you would get more and more computing power every couple of years. His initial analysis was every 1 year, and then he sort of redid his analysis, took in some more information, and made it every 2 years, which then led to one of his colleagues going, well, if it was 1 year, it's now 2 years, it must double every 18 months, is probably correct. That's not how exponential growth works. Okay, I'll just be clear on that. But actually, Moore's Law, it's not a law, okay? There's no reason why we should make computational power increase exponentially in this particular time period. And the answer is, of course, is that actually what happened is Moore pointed out that this was highly likely, and then what happened is it's become a target for production. This is how companies measure their success. Am I achieving, or are we achieving rather as a company, the doubling of computer power in some way? And that's led to other sort of related ideas of Moore's Law, the doubling of efficiency, so the amount of computations per unit energy, screen resolution, which we've seen through the smartphone revolution, the idea of going from very low resolution screens to extremely high resolution screens. And we're still continuing that because of the need for specialist scientific devices. Network capacity, storage capacity, these things have also doubled alongside. Okay, my first computer when I was was the envy of my department when I joined the software engineering group at a small company in Cambridge, the Technology Partnership, because I got the latest computer. It was a 100 megahertz, 100 megabyte hard drive PC, which everybody in the software group that I joined was sort of drooling over. And of course, that too has doubled, and we're now iPhones and gigahertz and gigabytes, and that's because of exponential growth. There's an inverse version of Moore's Law, of course, is that all of this computation comes at reduced cost, reduced energy consumption, reduced size, and so on. So there's sort of an inverse exponential shrinkage. So you might get the same computing power, but you're getting it on smaller and smaller and more efficient devices. So where's the future going with Moore's Law? I don't think Moore's Law is going away. It has that sociological imperative behind it still, but it's going to have to change. We've reached the limit more or less on transistor miniaturization because of power leakage, but we've got the multi-core, we've got the new architectures, and we've thought about these architectures in this department. But we're also looking at new technologies, and therefore potentially new laws. We're starting to see the quantum information, quantum computers are becoming real. 5 years ago, I think we just managed to stabilize some quantum bits. We've now got a production. I think Google has a sort of a quantum computer which has 8 quantum bits. Okay, I think I'm looking at Susan on the hope that she might know a little bit better than me, but I don't know. So we're starting to get real quantum computation happening, and you could imagine a Moore's Law coming behind that. We do quantum information in this department. We think about how we can use the spooky weirdness of quantum behavior into producing better quantum computation, but also for improving our ability to manage information. We could see similar things around robotics. Robotics are now, if you like, the peculiar odd things that we have. We've got a pepper in the reception as part of the events this week. Peppers are sort of a toy, a little bit of a show-off thing, but we can see maybe some Moore's Law of robotics coming through as we think collectively as a department about our work on robotics, about the miniaturization of robotics, under-actuated devices they're called. So basically, robots which are small and can't actually function very well, but you can make them behave in interesting ways. And if you get them small enough, you can put them inside your body and they can perform various functions like precisely delivering drugs or even cleaning arteries out and things like that. I'm speculating into the future. I have no idea that's what will happen, but you could see a Moore's Law that pushes robotics down to these smaller and smaller sizes and therefore enables innovation and technology to be developed in that way. And also learning in terms of thinking, sort of, again, only 10 years ago, deep learning was a myth. There was nothing like deep learning. We knew in principle it could be done, but it required enormous data sets that we didn't have. Well, Moore's Law caught up with that and gave us the enormous data sets. And so now people like Google have produced, essentially a standard system. You can use the API of TensorFlow to do your own deep learning over anything. Perhaps there's a Moore's law of learning that we can be thinking about as well, which is building on the algorithms and our ideas, our understandings of systems that can learn and actually learn in an explainable way as well. And that could be part of the future Moore's law that our work is thinking about. That's one invariant. I think there's another invariant. This is a bit of an indictment on human nature. Another invariant of human nature is inequality. It's a quote from the Christian Bible, Mark 14, you will always have the poor among you, and actually probably referenced directly back to Deuteronomy. So this is a 2,500-year-old invariant, inequality. We expect some people to be poor and some people to be better off. And you can look at the work, particularly I'm a keen on statistics, and you can look at the work of Hans Rosling, who worked for the World Health Organization. The world is getting less poor. Okay, there is hope for optimism in terms of the poverty, the number of people who are hungry on a daily basis, the number of people who have no access to healthcare or even to clean water. That's going down. Maybe not going down as fast as we can achieve. But nonetheless, when there's money to be made and power to be had, people will make sure there is inequality. And one of the modern inequalities is access to information. Okay? You can make people poor by being unable to access that information, whether it's information about their pensions, about benefits they could receive through government websites, or preventing them to get access to sort of modern banking. Okay? And you can prevent people from getting information in all sorts of ways. And I think our work on software engineering, particularly our model-based engineering, is a way of building excellent software so that we've got the right information in the right place, in the right form, to the right people. But we can also disable people. We can remove people from having the right access to that information. And so we work on accessibility. And that, again, touches on Helen Petry's award, looking at accessibility of devices. She's particularly focused on people with visual impairments and impairments due to old age, which is coming upon me not too far away. But we need to think about these things because there are people who are unable to access information as a result of either something they've been born with as an impairment that has then disabled them from access to information, such as a loss of sight, or what you acquire as old age, which is the inability to perhaps move a mouse confidently and precisely, so you can't click through to your internet banking and all of a sudden you can't pay the bills the way you used to. I think another way of, and we see this certainly in schools, we're thinking about literacy. We understand that literacy is a route out of poverty, okay? But I think there's a new literacy we need to think about, which is data literacy. We are a world awash with data thanks to Moore's law. And the risk of not understanding data is that people can tell you things and you don't know whether it's true or not. You can't understand the truth either because they're not telling you the truth, but they're hiding it in clever ways, or because you're just not sophisticated enough to understand what really happens when you look at real data and what that can actually mean and how to interpret it. And I'm enthusiastic about understanding statistics better and helping my students to understand statistics better, but we're also thinking about data science and the sharing of data in a way that other people can go out and make sense of it, be confident and literate in how that data is being used. And if you're not data literate, you can become impoverished because you don't really understand and you can be fooled by people who will tell you what they want you to hear. And of course, behind that information, we need to be secure. We need to have the basics of security to know that the information we've got is sound, is correct, and is not being corrupted for whatever reason, whether intentionally or even accidentally. And so when we are using that data to make sound decisions, we know what we're talking about. Related to that, as I said, Moore's law also talked about energy as important. As soon as you're processing information, you're using energy. Okay? You have to use energy in order to process information. And one of the challenges is that if you've got limited access to energy, then you have limited access to information. And so some of the work we're doing is thinking about energy, the energy usage to make sure we're minimizing our use of energy. This isn't just driven by climate change, the idea to conserve our resources, but also thinking about the ways in which information is being processed in small sensors which might be distributed in hard to access places. And we are thinking as a department all sorts of ways about our energy usage. The ISA building will have a solar farm which will be looked after by autonomous systems. This is led through work developed at the AIP. And it's called the Net Zero Project, and that will be about allowing us to have solar panel systems in places where you wouldn't really want to have people who have to look after them and staff the maintenance of those systems. We put them out into the world somewhere remote but sunny and get lots of power that way. Ian, various other people, Ian Wand, Alan, Neil here, they've all worked on the idea of efficient and reliable communications, and that involves the very, very efficient use of energy as well to make those things work effectively. We've also got fundamental changes to our use of technology. Think about things like reservoir computing. These are, if you're almost like using the accidental complexity of natural physical systems to allow you to do the computation for you. So you're not really using any energy to do a computation. You're just working out which bit of the system is the one that tells you the right answer. It's like magic. You kind of put in stuff in at one end, and it gives you a whole bunch of random answers. But if you work out which of those random answers is correct, you've got a computer. And this is Susan's work on reservoir computing is coming. These are all ways of saving energy and allowing information to flow more freely, because we don't have to use energy to get that information out to people. So inequality, we're thinking about the things which will address inequality, and I think which is something which we'll always have with us, but we should think about. I think we have to think also as a department, as an institution, to think about inequality. And now we are thinking very hard about this. Computer science is notoriously a male-dominated subject, very much so. It historically has been and continues to be so. 20% of our undergraduates, roughly 20% of our undergraduates are female. We're doing better than the national average in computer science. We're clearly not accessing all of the potentially brilliant computer scientists out there, okay? Because they're women. It's as simple as that. And it's worth noting, 100% of the heads of department are people who look like me, okay? White men, okay? I think we can do better. But how do you do better? It's not simply a case of just, it'll get better. It won't, because, human nature, we take the easy choices. In the IGGI PhD program, which Charlie mentioned, and which I currently lead, we do manage to get equality. About 50% of our students are female. Okay? But that has been through very conscious efforts, very, very much thinking about the breadth and diversity, not only of the students, but of the topics in which they're studying, so we can see that eventually there's a range of topics that are appealing to everyone, and therefore everybody can find their place within that program. But that's come with time. Our first intake was entirely white men. Okay, let's be really clear. So it's taken time for us to understand how that works. And I think really this is about sort of, I can't see a quick fix, because the real problem is that actually by the time we're getting to undergraduate admissions, that 20% is already in place. 80% of our applicants are men. Okay, so we need to be thinking about getting before the application point to get out of that problem of computer sciences for men, to be getting children at school to understand that actually computer science is for whoever's good at it. Okay? And whether you're a man or a woman, or you choose not to decide, that's up to you, and that's fine, and it doesn't matter, because it's not what computer science is about. So we need to think about our outreach, and we've been doing outreach as part of this week, but outreach is expensive. It's not what a higher education institution is designed to do. We have to think very carefully about how to do that and how to do that well. But I think for us, the real starting point would be to do that locally. Do it with the people around us, the people we see around us, and try to get them involved and think about widening the participation of those around us. Not to do computer science here at the University of York, that would be lovely, but to do computer science somewhere. To see that they themselves, whoever they are from whatever background, have the opportunity to go to university and study computer science and go on to do those great things that we've seen and heard about today. And I think some of that, and for us as a department, is also to build the right environment, to show that actually diversity is valued. And we're very fortunate to have the chair of the ACMW, the women's chapter of the ACM, the organisation that looks after a lot of the areas of computing. So Poonam's is the chair for that in the UK. And we've had events here as a result of her work. And actually, as a new member of staff, hitting the ground running and getting things going very quickly. And that's something we can build on. We've also established Array, which is essentially a social group for LGBT plus members of the department to get together and talk about the particular problems they face. I don't know what those problems are. I'm one of the white men. I'm one of the 100%. Okay, but there could be problems, and they've got a forum in which allows them to talk about it and to bring those things forward, and slowly through that to inform department policy, attitudes, and behaviours. This is an environment of diversity. Won't solve the problem overnight, but at least shows that there are ways forward where we can remove inequality. I think a third invariant is altruism. I don't quite know, that's not quite the right word. I struggle with this. It's about connecting, it's about people, it's about, I don't know, it's about understanding that we can make a difference to people. And touching upon what Charlie's sort of mentioned in the sort of founding fathers of the university, about the university for the work that we do is about ameliorating the human condition. And I think we touch upon the fact we are sitting in York, and York is a city built on Quaker values. The Terry's factory, the Roundtree's factory, and the way they treated their workers, and the way they, what they worked on. They made sweets because they didn't believe in making weapons. But these are all Quaker values that come through. And so I think actually we do have that principle in our belief of wanting to do better, to do something meaningful. But I think when we talk about meaningful work as a department, we're talking about doing something good, doing something better for people. We can help people to get each other's perspective. We look at games. Games are often thought of as frivolous, but actually by playing a game, you can briefly, in some small way, put yourself in the shoes of a different protagonist from yourself and see what the world looks like from their perspective. Whether it's a border guard in Papers, Please, or just seeing the world through a totally different perspective in something like Life is Strange. You get an experience of what it might be to be somebody other than you. And that's, of course, a way of understanding each other and a way of building a connection that allows us to think about how we might make the world better for different people. Communication is key. We need to understand the social networks, the social media that we've talked about. We've got data scientists looking at Twitter, looking at how information spreads and understanding what that means so we can connect and understand each other and recognize perhaps when people are misusing communication against us and protect ourselves from that and each other from that as well. And key to that is also privacy. A sort of a flip side, another aspect of security is to think about making sure the right information is in the right place, protecting people from harms by keeping their information about them safe. And so, for instance, one of the things I think is a really inspiring project or sort of a strand of work done in the department is thinking about secure online voting systems. If you've got a distributed rural community, participating in democracy is quite difficult, but if you can vote through your mobile device, lots of the world has a mobile device and connectivity. If you can vote and that vote is safe and secure and can't be traced back to you, but nonetheless is securely counted and can't be breached, then you can have really good democracy across the most challenging of country and landscapes and environments. And so I think security underpins that and enables us to have privacy. And I think that's a really important strand of work. So across these three invariants, I think of Moore's law, inequality and altruism, I think we're doing some really great work. But there's a disruptor. And the disruptor is automation. I don't know where automation is going. We talk about driverless cars, but you can also see a situation where actually what we don't need is cars at all. We need something which isn't cars, which uses some of the existing infrastructure, but has its own infrastructure in a different way. Maybe that's how automation is going to work. Okay? We don't know because it's really different. We don't really even have the modeling tools, the thinking tools, the legal tools, the economic tools to think about this in any succinct and effective way. Why is autonomy different? Because software typically is fixed into a device like this, or semi-fixed into a device like this. It's portable, but it's reasonably fixed. But autonomous agents are able to act in the social and physical world on their own. It's software that's able to act in our world, our human world, on its own basis. As a result of which, they do things differently. They don't necessarily understand our social world. Software isn't us. It doesn't grow up with us, develop our skills and our understandings, and therefore may act badly as a social actor or a physical actor because it doesn't understand what way we value. To understand this, we need really good new underpinning computer science. We need better computation. We need really more reliable AI, explainable AI, so we know what it's doing and it can tell us what it's doing. We need to be able to see out into the world and sense the world. Vision's a shorthand for all the different types of sensing we need. And again, we're doing that in this department. And we need robust sensing, and that sensing needs to be robust. We need to be able to rely on it and know that it's coming in at the right time and we can handle it in the right way in order to have the right information to work with and act autonomously. It needs to be safe, so it's reliable. We can guarantee the processing. We know it's going to work. We know when it's going to work. And if it's going to fail, we can prevent it failing catastrophically and damaging people and itself. It needs to be good. It needs to be the autonomy that we need, not the autonomy that other corporations and governments would like to impose upon us, drones that watch our every move autonomously. We don't want that. But what do we want? Well, we need to think about our ethics and how what we think of as good autonomy. And it needs to be secure, because the worst thing you can have is you've got lots of autonomous systems out there in the real world acting socially and physically, and then somebody takes them over for their own purposes. So we need to have security there. So the vision that I've started off with actually is fundamental to enabling this autonomous world to come into being. I have no idea what it will look like. I'm not sure anybody else does. People like John McDermott might have a good idea, but I'm not sure he does either. Yeah, there we go. So I'm not quite forecasting the future, but I'm showing what I think are invariants that we can keep in mind when we are thinking about our work, but also recognizing that things like automation and something else that nobody yet thought of properly may yet come along. But if we think about it in terms of what we're trying to do, what we're good at, we can maybe shape the future to be what we want it to be. But we mustn't forget we're sitting inside a university, and education amplifies what we do. Because through education, we are able to bring about a change. It's the sort of myth, isn't it, of the rhetoric around impact, research impact. Actually, everybody knows who's ever taught a student that your biggest impact on the world is actually through the students you send out into the world to go out and do something else. Okay? Phil Venables, he's having impact, okay? But he's just a student, so we taught him, so that doesn't count as impact. That's not right, okay? He's the department had impact through people like Phil and all of our graduates. And so we're educating undergraduates. We've got taught masters on campus and online, has been mentioned. We've got PhD students, specialist PhD students in CPD, continuing professional development has been mentioned already today. Of course, when you teach, it's not just the students who learn. I don't think there's any lecturer who, after a while hasn't had a moment where they're standing here on this stage very similar to this one, and they're explaining something and they suddenly realize for the first time what they're actually talking about. Okay? We learn through the ability to attempt to try and articulate the things we're not quite sure about, but we know we're going somewhere, and in the process of teaching it, we work it out better for ourselves, and that takes us on to the next stage. Education amplifies all aspects of our work. Of course, we also act, therefore, as a model for our principals. We encourage meaningful work in our students. We encourage collegiality. I think a lot of people have seen today and are commenting today on what a collegial department we are. It's a common comment I get as a head of department is we're a collegial department. We care about each other, we spend time together. We argue, but we also care about each other, and the arguments are part of moving forwards together as a college of people. And so we articulate and we embody those principles, and our students take those principles out with them. So what I can say is I can't see the future. I'm not even going to try. Go look at the internet, it might have an idea, okay? But what I can say is that looking at the department now, what we are doing now, I think between our principles, our vision of safe, ethical and secure computation, and the very active and lively work that I think is actively speaking to these sociological invariants, I think we have a very successful future ahead of us built on a really solid now, which has grown out of the previous 50 years that we've had. Thank you very much.